All right, chemistry class, welcome to another installment of our interactive reader videos. We are going to look at chapter 5 today. And as you can see from the title, we're looking at the periodic law. Obviously, we're going to be looking at the periodic table. Now, this is going to tie back into what we've been talking about. So it's really cool to see what you've been learning and how that's going to apply to what we're going to look at today. And these first two questions are going to ask you to just think about what you do know about the periodic table and what you've already learned. So go ahead and just pause this video and answer questions 1 and 2 at this time, to the best of your ability. Alright, hope you have been able to answer those two questions. Put them in your notebook. They should be in your notebook so that I can see them when you upload them and submit them. Okay? Alright, since we are going to talk about the periodic table, let's spend a moment and just look at the history of the periodic table. It's always helpful to understand a little bit about the background of what you're learning, and in this case, the periodic table. So let's just spend just a few minutes talking about kind of the development of the periodic table and some of the major players. So back in 1860, as you can see here, there were about 60 known elements. There are about 100 now, 60 known elements. But the scientists at that time didn't know a lot about those 60 elements. They learned a little bit about the properties and the compounds that they were forming, but they didn't have them organized in any particular pattern at that time. So, and even some of the different masses, the masses that scientists were coming up with were different for the different elements. So, finally, an Italian chemist, he presented a method for accurately measuring the relative masses of atoms. So this is just important because the next scientist who's important, who is considered the kind of the father of the periodic table, he was using those relative masses, those atomic masses, in order to kind of create a table or a chart and look for patterns. So along comes Dmitry Mendeleev. He's a Russian chemist, and he decided that he was going to use the atomic masses of each element, and that he was going to use that to help him organize the elements in a particular fashion. And he was going to use, in addition, the properties that he had discovered. So he started to work with all these different elements and see how they would react with other elements, and he started to see that some elements reacted in a very similar fashion. So he placed the name of each known element on a card, and he would put the atomic mass on there, and then he would write down any physical properties, like, for example, at what temperature would it boil, or was it shiny, was it a certain color, those physical properties, as well as the chemical properties. Did it react with oxygen? Did it react with water? Things like that. And then he began to arrange the cards according to increasing mass, and he started to see that there was a trend or a pattern. It might look something like this. Remember, he's got all these cards, right? He's got all these cards that have all the information for each element. He started to lay them out, and he noticed that when he put them according to increasing atomic mass, so here's hydrogen 1, and then you'll notice it skips up here to lithium 7. All right, there's some elements that maybe hadn't been discovered yet. And then 9, 11, 12, 14, 16, 19. You see how the masses are increasing here as you go down each of these columns, right? Those are the masses, not the atomic number. Those are the masses. Well, he also noticed that when he did this, that there were elements that had similar properties, and that pattern repeated itself. Okay? So he noticed that when the elements were arranged in increasing atomic mass, certain similarities in their properties appear at regular intervals over a certain number of elements, and then he'd realize, oh, now this element at the end of this row or this column is going to act like the one way back here, and I'm going to put them together. Okay? So for example, he found out that fluorine and chlorine, they behaved similarly. So let's look back up here. Here's fluorine, so he was arranging these by mass. He'd go down, increasing mass, and he was testing, looking at all the properties. Here's fluorine, and then he comes up here and see he comes down to more increasing mass. He goes, oh, chlorine and fluorine are similar in their properties. So he ends up putting them in this pattern, okay? He realized this for lots of different elements, and so he started to realize there is a pattern or a period, okay, repeating pattern. It's periodic. It's going to follow this certain flow or certain pattern all the time. So he started to arrange these elements in this table, and as a result, he kind of came up with this crude table. And you'll notice that it does kind of repeat itself. So you have these elements, and then these elements, and then it repeats itself, and he has these repeating pattern a little bit. And you'll also notice that there are some holes here. There are some holes in his periodic table. Well, that's because Mendeleev realized, here's an obvious one, he even put a question mark here. What he's basically saying is, you know what, there's a pattern here, but I'm missing some elements. He made a prediction that elements would be discovered that hadn't been discovered yet, and they would be placed in those holes. And it ended up being true, because this pattern has to repeat itself, and if there are some voids or some places where there looks like there'd be some missing elements, he said, we haven't discovered those yet, and we will discover those. And it was true. Those holes were actually ended up being real elements that we know of today, and he discovered that because of the pattern. Okay? So Mendeleev is given credit for discovering what is called the periodic law, and it basically says this: the physical and chemical properties of the elements are periodic functions, meaning they're going to repeat. There's going to be a pattern of their atomic numbers. Now, Mendeleev used atomic mass, but now we order the elements according to their atomic number. The atomic number, if you recall, is the number of protons. Okay? So now we organize the elements according to the number of protons in the nucleus, and the pattern is still there. You still see a repeating pattern where elements that have similar physical and chemical properties are going to be in the same group or the same family, and we'll see that on the periodic table. Okay? All right, so today our modern periodic table arranges the elements by both the atomic number and the properties. That atomic number is the number of protons, remember? And the properties end up falling into place as we see the similar properties and we put them in the same column. Okay? So you should have in your notes at this time, you should have the periodic law written down, and you can state it exactly the way it is, but also make a few extra comments there so you know some of the important marks of it. Okay? All right. The modern periodic table is an arrangement of the elements in order of their atomic number, remember that's the number of protons, so that the elements with similar properties fall into the same column or group. So when we look at the periodic table, we know that all of these elements in this group with nitrogen have similar properties. All of the elements in this group with oxygen have similar properties. Same thing here. This group here is called the halogens, fluorine, chlorine, etc. They all have similar properties. Okay? So let's talk just a little bit about some of those groups. The noble gases, that is the last column on the periodic table, and they all have similar properties. They do not like to react. They're pretty stable. They have a full outer shell of electrons. They're usually gases at room temperature, I believe, and so they all react in a similar manner. So the noble gases is one group that you should definitely know. They're also called the inert gases sometimes. Okay. Then we also have the lanthanides. The lanthanides are, let's see if we can get a periodic table here. The lanthanides are here on the periodic table. I'll show you really quickly. The lanthanides are this row right there, and actually the periodic table, this group here is often pulled out of the periodic table and put below, and then everything is compressed, but this group actually should fit in between those two elements right there. So this is La, that's lanthanum, and then it really should continue. You see 57 here, and then this is 58. So this should continue right there. So this group right here is called the lanthanides, following element number 57, lanthanum. And then up here, you have the actinides. And the actinides are the other group in that lower portion there that's pulled out. So this here, you see AC, actinide. These are going to be actinides then down here. Okay? I'm just pointing out a few different areas of the periodic table that you should be aware of. That's all. Okay? All right. Since it is called the periodic table does have a repeating pattern, as we mentioned. That's called periodicity. Okay? The periodicity of the atomic numbers is one of the most important features of the periodic table. So you're going to see a pattern not just in the physical and chemical properties, but also in the atomic number, how many protons, and also that means how many electrons in a neutral atom of that particular element. So it says consider the noble gases in group 18. Remember, those are the inert gases at the end. That's group 18. That's the 18th group all the way at the end. The first noble gas is helium. So right here, it has 2 protons in the nucleus. It also has 2 electrons. So its atomic number is 2. The next element in that similar property, in the same row, is neon. It has 10 protons in the nucleus, 10 electrons, and the difference between that is 8. So 10 minus 2 is 8. The next element that has similar properties is, so we said neon, and then we go to argon. Argon has 18 protons, or 18 electrons, and the difference between that is 8. 18 minus 10. Then we have krypton. There's 36 protons, 36 electrons. The difference between 36 and 18, the one right above it, is 18. And we keep going. We're down here to xenon, and xenon is 54. 54 minus 36, the one above it, is 18. And then we got radon. Radon has 86 protons, 86 electrons. The difference between that and the one above it is 32. And that is true now. If you go to any column, you're going to see the same 8, 8, 18, 18, 32 pattern. If we go to group 1, which is all the way on the other side of the periodic table, and we take and we subtract the atomic numbers of the one below and the one right above, of 2 elements in the same column, all right? 11 minus 3 is 8. 19 minus 11 is 8. 37 minus 19 is 18. 18, 32, the same as the pattern in any other group. Okay? So there is a pattern there in the atomic numbers. And that is because, if you remember from the previous chapter, we have these energy levels. And these energy levels are where the electrons reside, right? And there are only going to be a certain number of electrons at each energy level, and then they've got to go up to the next energy level. So it's like having floors of a building. You can only have a certain number of people in a particular floor, and then you got to go up to the next floor, and then the next floor, okay? All right, You don't have to answer these review questions. You can if you'd like to. We're going to answer all the chapter review questions at the end of this, okay? All right. Now, why? The question is, why do we have this pattern? Why do we have a pattern in the atomic number? Why do we have a repeating pattern in the properties of elements? Well, it all has to do with what we talked about before, and that is the electrons and the electron configuration, how the electrons are arranged. Remember, this is a crude model here, we've got these different energy levels. And I'm going to kind of draw it this way. It's a little more complex than this, but here's your nucleus in the center, and we've got these different energy levels. We got the first energy level, the second energy level, the third energy level, the fourth energy level. And if you remember, each energy level can accommodate more and more electrons and have more and more shapes or regions or orbitals. Remember, in the first energy level, we have the first energy level, and the only shape that can hold electrons in there is S, the sphere, and it can hold a maximum of 2 electrons. Well, when we get to the second energy level has a spherical shape that can hold a maximum of 2 electrons, but it also has 3 p orbitals, 3p shapes. And remember, there's an x, y, and z there. So each of the p's can hold 2. Well, 2 times 3 is 6. So you could have a maximum of 6 in the 2 p's. Now it's full. Now you'd have to go, if you have more electrons, if you go to another element that has more electrons, you'd have to go to the third energy level. It has an S, maximum of 2. It also has 3 p's, maximum of 6, but it also has D. So D has a maximum of, there are 5 D's, 2 in each of the D's, that's a maximum of 10. And you can see then we go to 4, S, 4, P, that'd be 2 here, 6, 4, D, 10, 4, F. You have 7 F's, so that's a maximum of 14 there. Now the arrangement of these is not quite the way I wrote it out. The 4S actually gets filled before the 3D, but we'll talk about that in a second. Okay? But you can see as you go to higher and higher energy levels, it can accommodate more and more electrons. All right? So it's this arrangement of electrons that give elements similar properties, the electron configuration. Okay? All right. The period of an element is determined by its electron configuration. Very, very important. You have to know the connection between the periodicity of the periodic table and the fact that that is because of the arrangement of the electrons. You have to know that. So if you want to pause this video and write this down right now, you've got to know that. Okay? So let's look a little bit at how this works out. All right. All right, we're going to look at the relationship between the period length and the sublevels being filled. Kind of like what I mentioned before, but we have a chart here to help us. Actually, what I think I'm going to do, I'm going to come down to the periodic table, and I'm going to show you how the repeating pattern of the periodic table relates to the electron configuration. Okay, so let's walk through this periodic table, and I'll show you that as we go across the row and down the column, you'll see that we get to see this pattern here of the electron configuration. So stay with me. This is crucial. This is where we're tying what we learned before about the arrangement of electrons, electron configuration, to the periodic table. Why is there a repeating pattern in the periodic table? It's because of the arrangement of the electrons. Watch. Here we go. So hydrogen has 1 proton. See the atomic number right here? 1 has 1 proton, and it has 1 electron in a neutral atom. So it just has 1 electron. Assuming that electrons are always going to fill the lowest energy levels first, where's that electron going to be? It's going to be at the first energy level, 1, and it's going to fill that only region in the first energy level, which is S, and there's going to be 1 electron in that 1s orbital. Okay? I come over here to helium. Helium has 2 electrons. 2 electrons, and that means it's going to be the first energy level, and it is going to be in that S-shaped orbital. There are going to be 2 electrons there. Now, the 1s orbital, every orbital can only hold 2 electrons. So that 1s orbital is full. It is full. It cannot accommodate any more. It will not let any more electrons come into the 1s orbital if it already has 2. Well, what happens then when we come to lithium? Lithium has 3 electrons. Well, then that third electron has to go to the next higher energy level. So this would be what? 1s2, that's where the first 2 electrons are, and then it has to go to 2, the second energy level, 2s1. Okay? Beryllium has 4 electrons. So that's going to be 1s2, 2s2, because you can have 2 electrons in each orbital. Okay? I'm going to come way over here to, actually I'm just going to do boron. Let's go continue going on here. 5. So boron is going to be what? Boron is going to be 1s2, 2s2, there are 4 electrons, and then 2p1. Carbon. Carbon is going to be, it's going to get a little messy here, but I kind of want to keep them in columns so you can see the similarities here. Carbon is going to be 1s2, 2s2, 2p2, okay, 2p2. Nitrogen has 7. It's going to be 1s2, 2s2, 2p3. Wait, why 3? I thought you could only have 2. Remember there are 3 different p orbitals? So the first p orbital was full here. I'm now filling the second p orbital. So that's why there's 3. Those 3 p orbitals can hold a maximum of 6. Alright? Oxygen. Oxygen. 1s2, 2s2, 2p4. Fluorine. 1s2, 2s2, 2p5. And then neon, 1s2, 2s2, 2p6. Full. P orbitals, there are 3 of them, 2 in each, can hold a maximum of 6, so now it's full. And in the second energy level, it only has S and P. So what is it going to do now when we have 11 electrons? It's going to have to go to the next energy level. 1s2, 2s2, 2p6, 3s1. Now, I'm going to pause here. As we go through this, you're going to see that the ending of every electron configuration in a column is similar. Look here. Hydrogen ends in S1 at the first energy level, 1s1. But look at lithium, 2s1. Look at sodium, 3s1. Everything in this column right here ends in S1. Now it might be at the first energy level, 1s1. It might be at the second energy level, 2s1. It might be at the third energy level, 3s1. Here, potassium is going to end in 4s1. Rubidium is going to end in 5s1. Cesium is going to end in 6s1. Francium is going to end in 7s1. They all have a similar ending to the periodic table. Okay? The ending, the outermost electrons are called the valence electrons. Those valence electrons. Those valence electrons are the ones that are involved in chemical reactions. So you can see if they have the same number of valence electrons, the same number of outer electrons, that means they're probably going to react in a similar fashion. Okay? Same thing over here. If I was to do magnesium right here, let's do magnesium. Magnesium is going to be 1s2, 2s2, 2p6, 3s2. Well look, beryllium right above it ends in 2s2. This ends in 3s2. All of these are going to end in something s2. Okay? Everything in the boron group is going to end in something P1. All of these are going to end in something P2. All of these are going to end in P3. All of these are going to end in P4. All of these, P5. And all of these are going to be full. They're going to end in P6, except for helium, because it is full after just the S. The one S is full. Okay? So you can see that all of these columns have similar endings in their periodic or in their electron configuration. They have more and more electrons, of course, but the ending, the number of outermost electrons, is very, very similar, and that's why they behave in a similar fashion. So when we look at the periodic table, groups 1 and 2 are filling the s orbitals. So this is called the s block. Right here, this is called the s block. Okay? Over here, this group, they are filling the p block. That's called the p block elements. And if we were to continue, you would notice that down here, this block right here, this is where you start to fill the d orbitals. So that's called the d block. And then this one down here, the lanthanides and actinides, that is your f block. That's where you're filling the f orbitals. And it corresponds to the number of electrons that each sub-level or each of those orbitals can hold. So remember, s can hold a maximum of 2. That's why there are 2 columns here. Remember, there are 3 p's. Each p orbital can hold 2, so 3 times 2 is 6. That's why there are 6 columns here. And there are 5 d orbitals. Well, each can hold 2, so 2 times 5 is 10. That's why you've got 10 columns in this group. And there are 7 f orbitals. 7 times 2 is 14. That's why you've got 14 columns here. Okay? So perfect correspondence, perfect kind of pattern. We now understand why this pattern exists and why the periodic table is arranged the way it is. It's all because of the electron configuration. It's all because all of the elements in each family have the same number of valence electrons. Okay? All right. So all of that is what's explained here in the rest of this section. And on the periodic table, I just want to make sure that when you read the periodic table, you know what all this information is. So here, every box in the periodic table, every element, this top number is your atomic number. That is the number of protons. You must know that. What that means is, this is its ID. This is its ID number. For aluminum, every aluminum atom always has 13 protons. Always, 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 always. It can have a different number of neutrons or different number of electrons, but it always has 13. Okay? Here's its symbol, 2 letters. There's the name. Here is the average atomic mass. Remember, this is a weighted average depending on the abundance of the different isotopes. And then here, it might include the electron configuration. Now, we're not going to write out the entire electron configuration. We abbreviate it. So you'll notice here we have the noble gas, and then whatever is going to be added on to that noble gas to get your aluminum configuration. Okay? Okay. So you now are experts on reading the periodic table. Okay? I also want you to know that the metals are all on the left of the periodic table. So on your, this is the left side of the periodic table here. These are your metals are going to be on the left side. And your non-metals are over here on the right side. And in between, you've got these elements that are kind of metals or non-metals. They can maybe act as both, depending on maybe what temperature they're at or other things. And those are called your metalloids. In between, a couple other important groups here. This group right here, this group of metals, those are called your, it's right here, those are called your alkali metals. And then you've got your alkaline earth metals. Alkaline earth metals are group 2. So I want you to know that these are your alkali, and these are your alkaline earth. Maybe you've heard of batteries, alkaline batteries. Alkaline batteries are made with these elements. Okay, or you've heard of lithium cadmium batteries. These batteries are used, or these elements are used in batteries. Okay. All right, so we've got metals on this side. We've got non-metals on the other side. I already mentioned that this group is halogens. You should know that. And this group is noble gases. And then the metals in the middle. Let me just pull up the periodic table here. These right here, the D block, these are also called your transition metals. They behave a little bit differently because of the D block. So they sometimes have a little bit different behavior, and we'll talk about those when we talk about ions and ionic compounds. Okay, so periodic table, a very, very powerful tool. We're going to be using it all the time, all the time, all the time, all the time. Okay, so the rest of this section here is again talking about the alkali metals, and it talks about some properties. You don't need to know the properties of all these different groups, but we'll come across them as we hopefully do some different investigations with them. Okay, I mentioned the alkali earth metals, and you'll notice that when we describe them, we talk a little bit about their properties. So for example, the alkali earth metals, what are they? They're a little harder and denser than the alkali metals. They have a higher melting points. They're less reactive than the alkali metals. Up here, the alkali metals, what do we know about them? Well, they're silvery in appearance. They're soft if you cut them with a knife. They're very reactive in water. Okay, so they have similar properties. That's how we know that they should be in the same group or the same family. Okay. A couple things here. Hydrogen. You'll notice that hydrogen is located. It's interesting. Hydrogen is located over here, but it is not a metal. It's located here in this family because it has one valence electron, just like lithium, sodium, potassium, etc. And so it's going to sometimes behave like a metal, react like a metal, even though it's not a metal. So it's in this family, but you kind of see that, you'll notice that it's a different color because it's not a metal. It is a gas at room temperature. Likewise, helium. Helium is a noble gas, but it's full when it just has 2 electrons versus the outer valence electrons being 6. So it does behave like these other noble gases because it's full. Its outer level is full. That's what's important about a noble gas. Okay? Outer level is full. Okay. I mentioned these transition metals already. Okay. We're not going to have to worry. We won't worry about that right there, but we will mention, as I already did, this. We already talked about the S block, where the S block is located. Okay. We already talked about the P block, where the P block is located. Okay. P block elements are in this group here, group 13 to 18. We mentioned that. We mentioned the halogens already. We mentioned the lanthanides and actinides. Okay. There's another problem. So that takes care of section 5.2. You don't have to answer these questions. We're going to go on to 5.3, and then we're going to look at, and then you'll answer the review questions at the end of the chapter. Okay. All right. So let's continue to talk a little bit about the electron configuration and the periodic properties. When we look at the size of an atom, we talk about the atomic radius. So the atomic radii are related to electron configuration. So we define the atomic radius, how big an atom is, as saying that if you were to have 2 of those atoms together, so this is a chlorine atom here, this is a chlorine atom here, they're bonded together. And the distance between the two nuclei, half of that would then be the atomic radius of chlorine. That's what they're saying. It's 1/2 of the distance between the nuclei of identical atoms that are bonded together. Okay? Now, why is that important? Because there's a trend in the atomic radius on the periodic table. Okay? So there's a gradual decrease in the atomic radius as you move from left to right. And we'll talk about these trends here on the periodic table. So as you move across the periodic table from left to right, the radius, the size of the atom, I'm just going to put size here, the size of the atom decreases. Okay? As you move down a group, the size increases because you're going to higher and higher energy levels. Okay? Size of the atom, how big the atom is. Okay? Now, let's just talk about a second why that is. Why would the size decrease as you move across a particular row? That's because you have more and more protons. More protons, more positive protons in the nucleus are going to pull in the atom. It's going to pull in those electrons and make it a little tighter. Okay? Positive protons and negative electrons. If I have a nucleus here and it has a whole bunch of positive protons in it, it's going to pull those electrons in tighter. It's going to pull them in tighter. If I just have one proton or two protons in the nucleus, then those electrons are going to be a little further away. It's not going to have as strong as a pull. Okay? So as you increase the number of protons across a row, across one single row, more protons mean you're going to have a smaller and smaller atom. Size decreases as you go across the row. Why does it increase when you go down a column? That's because you're jumping to the next energy level. The electrons are going to go to the next energy level, and then the third energy level, and the fourth energy level as you move down a particular column or family. Okay? So, basically the trend here for the size of atoms is this. You'll notice the smallest atoms are up here. Smallest atoms, the largest ones are down here. Okay, so we kind of draw sometimes a diagonal arrow like this, and this is decreasing. Decreasing size. Decreasing size. Smallest ones up here, largest ones up there, down there. Okay? So that's going to be important in how they react. So smallest atoms up here, they like to gain electrons. They like to bring electrons in tight. Their atom is small, so that means if another electron comes in, it can grab that electron and keep it close to its nucleus. Okay? Out here, they tend to lose electrons because over here these metals are larger and they tend to lose electrons as a result of their outer electrons being far away. And so more electrons come, there's not much of an attraction to the nucleus. Okay? These like to gain electrons. These are all your nonmetals. Nonmetals like to gain electrons, and these like to lose electrons. Metals like to lose electrons. These are metals over here. Okay? Nonmetals over here. Okay. We're not going to worry about this right now. Don't worry about that. Okay, the other trend that we want to look at is something called ionization energy. And it all, again, goes back to the size of the atom. Ionization energy, I want you to write this down in your notes, is the energy required to remove one electron. Okay? So, again, let's go to size of the atom. If you've got an atom and the electrons are really close, really tight, and you have another one where the electrons are further away, okay? Well, if there's an attraction between electron and proton here, which one is going to be easier to remove? the smaller atom is going to hold its electrons tightly. If I'm holding on to something, I'm going to bring it now. I want to keep it. I'm going to hold it really close to my body, and you're going to have a hard time getting it away from me. But if I have it stretched out far, far away from myself, holding it out here loosely, then it's going to be easier to take. So ionization energy, which one of these situations is going to be easier to take away the electron? Well, this one over here, this electron is going to be easier to steal because it's further from its positive nucleus, positive protons. So small, large, the ionization energy here, I'm just going to put IE for ionization energy, is going to be greater. Over here, the ionization energy is going to be smaller. Harder to take this electron away from the atom compared to this one here where the electron is further away. Okay? So for ionization energy, we often draw an arrow, again this way, but it's increasing. Here the increasing, okay? Increasing. Ionization energy gets bigger. And this is a chart that just shows that. You don't need to know that. Okay? Okay, let's look at those are some ionization energies. Okay, let's look at one more thing. This is called electron affinity. You need to write this definition down. It's the energy change that occurs when a neutral atom gains an electron. Okay, to gain an electron. And again, this is going to relate back to the size of the atom. So here you'll notice that now these numbers are negative. You don't have to worry about why they're negative. It's just that they're losing energy. But basically, the electron affinities for atoms that gain energy when gaining electrons are difficult to determine. All right. So basically, if it loses a lot of energy when it comes into a new atom, it's going to give off, and that giving off, that's where we use a negative number for that. Okay. So here's the idea, though, is that you can imagine that if this atom here wants to really gain this electron, and then that electron is going to lose a lot of energy when it is joining that atom, okay? It's the energy change that occurs when a neutral atom gains an electron, all right? So basically, if a lot of energy is given off when this atom here gains an electron, then it has a large electron affinity. Affinity basically just means attraction. Let's just deal with it that way. So in one sense, the ionization energy before is taking away an electron. Here we're going to add electron. But they're very similar because we're talking about, in this case, the amount of energy that is released. So here we have, you'll notice that we have a very large amount of energy released. Again, the negative number is just telling you that it's released. A large amount of energy released when fluorine gains an electron. So again, this is increasing. Why would that be? Because the smaller atoms can really pull in electrons, and as a result, give off a lot of energy when they add electrons. Okay? I'm going to sum this all up in just a little bit. When you gain or lose electrons, remember that you're forming ions. So you need to know that a cation is when you are losing electrons. This is losing electrons. And an anion is a negative ion. That's when you're gaining electrons. You must know that. Okay? I'm not going to ask you to know about the ionic radii at this time, so you don't have to worry about that. Okay? Alright, so what I want you to be able to do here is understand some of the trends, how the periodic table is arranged, and how it relates to electron configuration. Okay? When we talk about valence electrons, remember these are the outermost ones. outermost electrons, and they are the ones that are going to be lost, gained, or shared. In other words, they're the ones that are involved in bonding. You must know this. These are the ones that are involved in bonding. Okay? And here's the pattern. Remember, everything in group 1, they're going to end in something S1. They have one valence electron. Everything in group 2, they're going to end in something S2. They're going to have two valence electrons. Now we're going to skip over all the transition metals because there's some exceptions and some variations there. If we go to group 13, they all end in something P1. And they're going to have three valence electrons. They're going to end in S2, something like might be the first energy level, the second energy level. Sorry, it would be the second energy level, third, fourth, etc. They're going to end in S2P1. S2P1, three valence electrons. The fourth energy level, or the fourth group, I'm sorry, the 14th family is going to end in something S2P2, four valence electrons. The 15th group is going to end in S2P3, has five valence electrons. The 16th group is always going to end in something, this is the N here, is the energy level, S2P4, six valence electrons. 17th group, this would be your halogens, S2P5, seven valence electrons, and the 18th group is going to end in something S2P6. It has eight valence electrons, except for helium. Helium only has two valence electrons because it's full in the 1s orbital. Okay? All right. One other trend that I want you to know is called electronegativity. It's the measure of the ability of an atom in a chemical compound to attract electrons from another atom. Again, attracting electrons. Well, who's going to have the biggest attraction on electrons? The smallest atoms. The smallest atoms. Okay? So here I'm going to sum this up for you very quickly. Let me see if I can get a periodic table here to sum this up for you. Oh, let me do this. Let me go back to this periodic table right here. Okay? And I'm going to show you the different trends that we just talked about. So, atomic radius, that's the size of the atom, and basically the smallest ones are up here, smallest, largest. So I'm going to draw an arrow. I'm going to draw it the opposite way that I did before. Okay, here going down, increasing in size. Okay, increasing size. Now, what are all the other trends? Let's look at ionization energy. Ionization energy talked about how hard is it to pull away an electron, the outermost electron. Well, the smallest ones are going to have the tightest pull, the tightest hold on electrons. So that means the arrow goes the other direction. This is increasing. Increasing IE. Okay? Then we looked at affinity. Affinity is how much energy is released when it gains an electron. Affinity means, again, a small atom is going to really pull in other electrons, and it's going to attract them. It's going to release a lot of energy. And so this also is increasing this direction. Increasing affinity. Okay? And the other one was electronegativity. Electronegativity is when an atom and another atom are together, which one's going to pull more tightly or more strongly on those electrons, those shared electrons. And again, the smaller atom is going to be able to pull with greater strength. So this is increasing electronegativity. So you'll notice the smallest atoms have the highest ionization energy, have the greatest attraction for electrons, they have the greatest pull on electrons. All of these are increasing towards the smallest atom. And the size of the atom, smallest up here in this corner, largest down here in this corner. Okay? That basically wraps up the trends. That's what you need to know about the trends right there, okay, on the periodic table. All right. That is what there is. That's basically 5.3 right there. That's what I want you to know for 5.3. Okay? Let me just mention one other thing really quickly here. In the order of the filling of the orbitals, you need to know the order in which they are filled. There's a little exception. Remember I showed you this trick here. You're going to write out your orbitals, 1s, then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, etc. We'd have more here, but we don't need them, okay, in the 5th energy level, and the 6th and the 7th. So you write them out like this, and then to figure out in which order they get filled, all you do is you draw diagonal arrows across this. So the 1s orbital gets filled first, then the 2s, then you come back up here, 2p, 3s, 3p. This is where it gets different. You would think maybe the 3rd energy level would all get filled before the 4th, but it's just not the case. So I don't know why they named this a 3D when the 4s gets filled first, but it's just the case. Then 4s, then we come back up here to 3d, 4p, 5s, 4d, 5p, 6s, and so on. Okay? And this just corresponds to the periodic table. Let's come back up here to the periodic table and see how this matches with the periodic table. Okay? So on the periodic table, I'm going to go way back up here for a second. On our periodic table, we know which orbitals are going to get filled just by looking at the periodic table. So here in this first row, 1s is getting filled. Then we're going to fill the 2s, then the 2p, then the 3s, then the 3p, then the 4s. Remember, this is the S block. Now here in the center section is where we start to fill the d. Well, the first d is in the 3rd orbital. So I know we're in the 4th row, but this is the 3d, and then 4p, 5s, 4d, 5p, 6s, 5d. Oops, I should actually come here. This is 5d. This is actually 4f. We got to come down here. 4f, then 5d, then 6p, 7s, then we come down here, this would be 5f, 6d, and we don't have any more elements. So I know it's confusing, but basically the s is always going to be the same as the row number, so this is 1s. The p is also going to be the same as the row number, so this is 2p, 3p, 4p, 5p, 6p. But the d is always going to be one less than the row number. This is 3d. This is 4d in the 5th row. This is 5d. This is 6d. And the f orbitals are going to be 2 less than the row number. This actually is 4f, my fault. 4f in the 6th row and 5f in the 7th row. Okay? So it's an unfortunate naming. It's a little confusing, but that's how it works out. Okay, that is going to wrap up Chapter 5, ladies and gentlemen. You have to take time right now and answer these Chapter 5 review questions in your notebook. I need to see not just your notes, but also these review questions. And I provide you with the answers in the assignment to do that. Okay? As always, if you've got questions, please don't hesitate. We'll talk about these in our afternoon live sessions and hopefully clear up any confusion that you might have. All right, great job. Keep up the good work. Let me know if you have any questions or any problems.